So I'd like to introduce today's speaker, Professor Thomas J. Meyer, very distinguished professor of US, and he has a very long professor named Arey, Distinguished Professor of Chemistry, Solar Fuel Energy from the Research Center, University of North Carolina, Chapel Hill. And he graduated from Ohio University in 1963. He got a PhD in 1966 in Stanford University. He became assistant professor in North Carolina in 1968. Became associate professor in 1972 and became a full professor in 1975. Very quick promotion. And then since then he had been a professor until 2002. He has been professor in North Carolina, and he once moved to direct research at the Los Alamos National Laboratory during 2002-2004. Then he went back to North Carolina again, Chapel Hill, and he's now director of University of UNC Energy Frontier Research Center. So he has many awards, so I cannot explain that. But unfortunately, this time he's just came into Fukuoka, and after his talk he has to go jump to Fukuoka airport again to move to Osaka. So that's very unfortunate. But that's coming from the reason that he's going to be awarded a new award in Israel, which is called Samson Prize in Israel. It's awarded for research on new fuels and sources, as he explained to me. So anyway, to save the time for his talk, I'd like to start inviting him for his talk. So he's going to talk us about today making oxygen from sunlight and water. So Professor Tom Meyer, please.
Professor Sakai. It's a pleasure to be here. I apologize for not being here longer to get to meet some of you. I would have enjoyed that very much, but I have a very hectic travel schedule at the moment. I thought today, given the nature of the Institute, it would be appropriate to develop this thought about what does it take, chemically, technologically, material science, to be able to take sunlight and water and from them make hydrogen. I know that's a great interest. It's one part of what the Institute does. So let me develop that theme today. And let me begin with the answer, at least the answer at the moment for us. And the answer is, as you can see at the bottom, a mesoporous nanoparticle film. And there are red dots on the film. And the red dots turn out to be magic molecules that have special properties so that sunlight strikes the film, the complex assembly that includes both light absorption, as you'll see, and catalysis then responds and makes oxygen from water. And that's the target. Let's look at this, though, broadly and generally. Let me first develop and/or remind you of the importance of this subject for all of us. There are two key reasons why there's such a strong interest now in energy research, and one of them is energy supply. If you look at world energy demands and project ahead, starting where we are here and looking backwards, over a period of 20 years, energy use in the world doubled. It is projected that energy use will increase by 60% again by 2040. And the obvious question then is, where will the energy come from? If you look at the increase in demand, by the way, almost all of it will come from the so-called developing nations, not the US, Japan, or Europe. And in many ways, this is a very healthy sign because there are many correlations between human well-being and energy use. There's another part of this energy supply story. However, to consider, and that is that currently, internationally, over 85% of the world's energy supply is from hydrocarbons. And that poses other problems. Those problems are called climate change. And I remind you of certain facts about the relationship between hydrocarbons and climate change. When hydrocarbons burn, carbon dioxide is a product. When hydrocarbons are extracted, hydrocarbons are released. But carbon dioxide itself, although it has a very uninteresting infrared spectrum, is a real problem because once it reaches the atmosphere, there are no really good, efficient, rapid ways to take it out of the atmosphere, whereas hydrocarbons decompose quickly. And if you look at the facts, in May 2013, hydrocarbon levels reached 400 parts per million, highest in 3 million years. That doesn't mean much to you, but when I was at Los Alamos, one of the parts of the research portfolio I paid attention to was climate change modeling. Our responsibility for the national effort, the international effort, was to look at the oceans. But it was said back then, this was 10 years ago, that when CO2 levels reach 400 parts per million, be very careful because the models predicted uncertainties in weather and some of the extreme weather patterns that we've had lately may well be in part attributed to this source. So when the hydrocarbons burn, greenhouse gases get produced. One impact of that is a warming of the atmosphere, the greenhouse gas effect. Light gets absorbed, it gets re-emitted in the infrared in outer space. Molecules vibrate, they emit light. And if you look at the Earth from outer space, it is an infrared emitter. But some of that light strikes a CO2 molecule, gets absorbed and re-emitted. And that traps the light in the atmosphere. And because of that, temperatures are rising. If the temperatures, it's predicted conservatively that sea level rise could be 6 to 7 feet, a couple of meters by the end of the semester. By 2070, by projection, that could lead to 150 million people in port cities displaced. These are flood maps. You can find these on the internet. If New York sees sea level rises of 5 feet, you can see that most of it is inundated, Manhattan. Shanghai is built on a river delta. 70% of Shanghai will be underwater at 2 meters. So there are serious economic consequences, according to these predictions. There are ways to begin to think about this strategically and how to deal with it. And I know you have an important public policy component to your program here. And this is the kind of thinking that we used to do, again, when I was in charge of this research program at Los Alamos. There are a number of different energy sources and options. And one way to think about it is where are we now and where should we be in the future? And how do we make a transition from now to the future? Amongst the energy sources, the obvious one, efficiency and conservation. That's happening now. Gas mileages for cars are going up. Houses are becoming more efficient. As the costs for energy rise, part of that takes care of itself. But all these hydrocarbon sources that we have, and many, many more now emerging, in order for them to be convenient and at the same time consistent with a stable atmosphere, means we will have to develop this whole concept of carbon dioxide capture and storage. And I know that's an important part of your program here. Nuclear is another part. But at the very bottom is the place we all know we should get to as soon as we can. And that's renewable energy. Those energy sources that we use over and over again. And amongst those is solar. Of course, the energy comes from the sun, but the sun is predicted to last billions of years. And so we can assume that as a stable energy source in these calculations. Let's follow the lead on this. I intend to really focus my attention in this talk on solar energy and in particular an approach to this that goes back to the very first slide, based on chemistry and material science. So let's look at this energy source, the sun, in a little more detail. And when you look at it in detail, at first glance, it appears very positive. There is a great deal of sunlight. The Earth as a globe, if you look at all the captured sunlight as energy in the globe, it's huge. but only a small fraction can be used. For example, if you look at the globe, it's mainly oceans with a few brown patches called continents. So that means a lot of the space is not easily used. The sun is also very diffuse. In fact, it's a lousy light source. It's a terrible light source. What that means is you have to collect the energy to use it. So looking again at the US as a test case, that box is the area in the US. If you had a 10% efficient device and you wanted to capture all the energy needed today in the US, you would have to build a collector that big. That big is as big as the state I live in, North Carolina. Object lesson number 1, pay attention to cost in the very beginning and think about this in different ways. There's another problem with the sun, and that is it's intermittent. Sometimes it's here, sometimes it's not. It's a rainy day. There isn't much sunlight. Clouds. If the cloud passes over your solar collector, the efficiency falls very quickly. Even worse, the sun goes down at night. The sun goes down. It is not a continuous energy source. Unless you combine the sun with energy storage on massive scales, it can never, ever be a primary energy source. So, that leads us closer to the story that I want to tell, this combination of chemistry and material science. And that leads us to this thought notion of solar fuels and artificial photosynthesis. And so let's follow the lead on that and think about this first from the chemical point of view, what the targets might be, and see how far we can take the idea. The target reactions here are pretty straightforward. The simplest one is just to take water and split it into its components, hydrogen and oxygen. And the reason why that's a good reaction is that when they recombine, immense amounts of energy are released by formation of the OH bond. And so this is a way to store huge amounts of energy in chemical bonds in very compacted form. Another target would be to reduce carbon dioxide to anything, almost anything. Here's a reaction: use water as the reducing agent, reduce carbon dioxide in the end, all the way to hydrocarbons. And I'll show you can begin to think about that even now. The other product being oxygen, huge amounts of energy storage. So the thought is, one approach, as we'll see, will be to go back to this hybrid approach, molecules plus oxides, and in the end convert them into panels with appropriate pipes and plumbing to be able to carry out these reactions. If you think about chemistry of this kind, it's called artificial photosynthesis for good reason. There is something called photosynthesis, which isn't working very well today because there isn't much sunlight, but which has been working for a long time and is effective. So let's look at it first and see what we can learn about the natural photosynthetic apparatus. It occurs in something called the thylakoid membrane. Here are these particles, these particles called chloroplasts. We find them in green leaves, in the cell walls. As you can see, they're about 5 microns across, 1 to 1,000 per cell. And if you look at these little compartments and open them up and look at the membrane, it looks like that. And that is a photosynthetic apparatus. There are 5 key parts plus a part to convert ADP to ATP. This is photosystem 2 in a cartoon version. Light, in fact, I'll come back to this in a moment. Light is absorbed in photosystem 2, and in the end, water is oxidized to oxygen. That's where half of our reaction lies. So this is terrific. There are some problems with the photosynthetic system. If you're a plant, it's fine, it works. But for us, it's not encouraging that primary processes are not efficient. If you have a plant and it's 1% efficient at producing biomass, that's pretty good. Highly engineered plants can get up to 2 or 3%. But the plant doesn't care about making biomass. It cares about signaling and growing and doing many things. So biomass production is inherently inefficient. There's something else about this system that is really worth noting, and that is that, take that piece, photosystem 2. It has not changed in 2.5 billion years. hasn't changed one atom in 2.5 billion years. All around, the plants have changed immensely. Photosystem 2 has not changed. The second lesson about photosynthesis is, as wonderful as it is, it's highly integrated and it's very complex. If you change almost anything, it stops working very efficiently. And just a lesson for those of you who don't know anything about photosystem 2. It really is a remarkable series of events. Here is the thylakoid membrane, cartoon version of photosystem 2. There are antenna parts on the outside, chlorophylls and other pigments. They absorb the light and very efficiently funnel it into a chlorophyll P680. And here shows the structure of it from this wonderful structure that was done initially several years ago, back in 2005. So the light gets funneled to it. It makes a singlet excited state. It undergoes rapid electron transfer, first to a pheophytin, the porphyrin derivative, and then it undergoes further oxidation to a quinone, where quinone gets reduced to semiquinone. That drives a proton into the membrane from the top. Following that, the oxidized site electron transfer occurs. That leaves behind a porphyrin radical cation, this P680+. It's unstable in this environment for any long period of time, but it undergoes rapid electron transfer from a phenol, this tyrosine. The tyrosine is hydrogen bonded to a histidine. It's actually a so-called proton-coupled electron transfer, proton transfer. That radical then, in a much slower time scale, starts the process of oxidative activation of the oxygen-evolving complex, 4 manganese and a calcium in a cluster. That oxidation then triggers proton loss. So in the first stage of photosynthesis, it has to absorb photons, 4 photons, S0 to S1. There are 5 steps. Electron transfer occurs over 50 angstroms. A proton comes in, a proton comes out with one photon. If you look at this system, it's really quite remarkable, however, clearly difficult to duplicate. We need something far simpler. And something far simpler, in fact, came from Japan, at least the thought came from Japan. A now famous experiment by 2 scientists called Honda and Fujishima. This was back in 1972, so-called photoelectrochemistry. And what they showed was that you could take TiO₂, and if you shine light on TiO₂ and connect it in a circuit with a platinum electrode, there is net current flow. The TiO₂ absorbs high-energy photons. That releases electrons that go to a platinum electrode where protons are reduced to hydrogen. The key to this at the photoelectrode is so-called band gap excitation. TiO₂ is a paint pigment. It's in these walls in large amounts. It's very abundant. And what happens when it absorbs light is the band gap excitation produces a hole electron pair. And the hole is very strongly oxidized. It very quickly goes to the surface where it oxidizes water to something like a hydroxy radical. And that's the key to the success of the device. It's a terrific device, but there's a problem. It only works in ultraviolet light. The TiO₂ is white. It doesn't absorb visible light. It also requires a slight bias, and this is required to make the conduction band sufficiently negative to completely drive proton reduction to hydrogen. However, this certainly stimulated a lot of thinking, a lot of experiments, and it obeys rule number 1. Keep it simple. Keep it simple. 60,000 square miles later for your solar collector. There was another observation at the same time frame. It actually came from my group in collaboration with my friend Dave Whitten at UNC many years ago. And what we showed using flash photolysis was that you could take this transition metal complex, the famous ruvitnite, which is coordinatively stable. It absorbs light in the visible. Here's the absorption spectrum. Notice here's 400 nanometers, here's 500. So in the visible part of the spectrum, at least the high energy part, it's a respectable light absorber. And that gives it excited state, a so-called metal to ligand charge transfer state. If you look at the electronic description, the photon drives an electron from an orbital that's mainly on the metal to one that's mainly on the ligand. Therefore, metal to ligand charge transfer. The excited state lasts a microsecond in solution. If in the solution you add a couple millimolar of an electron acceptor, in this case methyl biologen, so it's just a 4,4' bipyridine methylated twice. Electron transfer quenching of the excited state occurs to give the oxidized form of the complex and the reduced form of methyl biologen. That was back then quite a feat. Valery and his work and his group in Germany had shown organic electron transfer and had done some very elegant work. This was a nice straightforward example using flash photolysis of what the products were. We could also estimate what the efficiencies were. But then we could estimate something else, and it really began something new, a new way of thinking. And that is, if you look at this complex ruthenium-3 and look at its redox potential, because you could do that by electrochemical experiment very easily, it was 1.26 volts. That means that that complex, after it's oxidized, is capable of doing water oxidation over the whole pH range, from 0 to 14. Methyl biologen, once reduced, Mv+, is a sufficiently good reducing agent to reduce protons to hydrogen. Ken just told me today about an experiment where they, in fact, are doing just that, using that as a reducing agent. So this was a terrific observation, but there is a problem. You can't stop here. And we were well aware of this way back then. We started thinking about how to move this forward. Because there are two big problems. One of them, this all works, but what it leads to in the end is a separated ruthenium-3 and methyl biologen in an isotropic homogeneous solution. And what happens next is they just diffuse back together. Back electron transfer occurs, and all this wonderfully stored transient energy is used up as heat, just heating up the solution. So we needed an architecture. We needed some way to build these components into a molecular system, but keep them apart and use them separately. There was another problem, and that was, even though this reaction, in that sense, is water splitting, if you look at the half of the reaction, water oxidation, there were no catalysts for water oxidation at all. Nobody had ever invented anything of that kind. So from the very beginning, there were a series of challenges. And let me walk you through these challenges. And let's first start with the water oxidation challenge. And you'll see this story evolve as I go through my talk later. Let me just, in a quick summary, and there's a lot of information here, but there's some important information. Just describe how this chemistry emerged. The first example of designed water oxidation catalyst was this one. Notice there are 2 bipyridines, 2 rutheniums in this case, oxo bridge, and 2 water. The key to this in the end will be you have to have a water in the coordination sphere at some point to do water oxidation, perhaps not a big surprise. This first observation was back in 1982. This field has evolved very quickly, especially of late. And let me just focus, instead of on this more complex system, an example of a single site catalyst. Notice bipyridine ligands again. Here's a pyridine carbene. And you'll see me use this complex 2 or 3 times more as I go on, so let me use it as an example. There's the water in the coordination sphere. If you look at the rate of water oxidation, the rate of turnover with this system and what it does do water oxidation. It's relatively fast. I'll show you some data later. It is very robust. If you have an electrochemical experiment, for example, you can turn it over hundreds or certainly tens of thousands of times. But let's look at how this system works and gain some understanding about the underlying reactivity. And this is an area that Ken has been a very significant figure in. So let's start with the complex, and let me just focus for the moment on the ruthenium aqua bond. I would point out to you that when you look at the periodic table, though, if you ask the question, why do people do so much ruthenium chemistry, it's in the second transition series. It's just below iron. And it has this wonderful property that you can do the synthetic chemistry and make complexes, but after you make them in these coordination environments, they tend to be coordinatively stable in multiple oxidation states. all the way from 2 to 6. If you tried these tricks with iron, they simply wouldn't work. Iron complexes would fall apart. So there are special characteristics here built into ruthenium that dictate the fact that many people study these systems in this way. Anyway, go back to the overall water oxidation cycle. And first thing to notice is it's complicated. And people complain it's complicated. But look at the net reaction. You have to take 2 water molecules, take away 4 electrons and 4 protons. There's no choice. In order to complete the reaction, you have to have complexity at an oxide surface with any molecule in photosynthesis. First step with this as a catalyst is oxidation to ruthenium-3. And you can monitor that electrochemically or by chemical mixing experiments using strong oxidizing agents. It then goes on next in the second step. Notice we've lost 2 electrons to ruthenium-4. And then something else emerges that we didn't know anything about before, called proton-coupled electron transfer. Look at what happens here. Here's an aqua, it oxidizes, but the pK of that water group, if you do a titration, is typically 9 to 10 in these complexes. Once you oxidize the ruthenium-3, depending on the coordination environment, the coordinated water becomes much more acidic. And so at any decent pH, ruthenium-3 is now a hydroxy form. When you go to ruthenium-4, the characteristic coordination sphere is to have an oxide group with real multiple bonding between the ruthenium and the oxygen. What's happened is that as the metal gets electron deficient, the OH protons become more acidic. When they leave, they open up p electron density for donation back to the ruthenium. That is a key because with the oxide group, it opens up reactivity channels that are well known. Oxygen atom transfer to phosphates or sulfides. And as we'll see in a moment, we're to water molecules. One key to this, though, notice in that activation process to get to the active form is there's no increase in charge. If you try that trick without having associated protons with a complex in this series, the difference in potential between the 2 couples would be between 1 and 1.5 volts. Proton-coupled electron transfer allows you to accumulate charges, oxidation states without increasing charges. So you can build up multiple redox equivalents in one place. Anyway, ruthenium-4, if the thermodynamics are right, can do water oxidation. In this case, it's much faster to take away an additional electron. To go to ruthenium-5, if you're a transition metal chemist, it's now at D3. And in most of these cycles, the rate-limiting step then is next. Oxo-atom attack on a water molecule, and I'll come back and say more about that mechanistically. To give an intermediate hydroperoxide, it oxidizes further to ruthenium-4 peroxide, and we have really good spectroscopy and a lot of evidence for these as intermediates. No crystal structure yet in these coordination environments. Then an oxygen is lost and the complex re-enters the cycle. And or sometimes the system actually can be hung up here. This can be the rate-limiting step, the loss of the oxygen. And one way to avoid that is just oxidize it again at an accessible potential, it turns out, to give ruthenium-5, and then oxygen comes out of the coordination sphere and the system re-enters the cycle here. So we know a lot about that part. What about the architecture part? After looking at this problem for some time, for the first example of what I described here as a dye-sensitized photoelectrosynthesis cell, or DSPEC, the first example like this was published back in 1999. And the thought was this: let's build on what is known in dye-sensitized solar cells, where you take TiO₂ again, that old trend, and you coordinate to it a chromophore. So here's one of these Rubimby chromophores, just disguised. But now put groups on the complex that allow it to form chemical links to the surface. When you do that, if you do excitation, you make an excited state, and the system is perfectly happy. But the excited state is now an enhanced reducing agent and has the ability to undergo electron injection into the conduction band of this optically transparent white TiO₂. That initiates a series of events where you want the electron to transfer to a second electrode, where reductive chemistry can occur. And for us, we want to reduce protons to hydrogen. So instead of trying to do photocurrent, the thought we had was, since we want to do artificial photosynthesis, just make the molecule more complicated. And so I will show you later this very molecule, and we'll do a lot with it. And that very molecule, notice, has a chromophore right. You know a lot about that, a lot about the excited state. I'll say more later. Once now injection has occurred, the chromophore is oxidized. Electron transfer can occur from outside to inside. And that begins the process of oxidation. Recall, for the next net reaction, we have to do this 4 times. But we already have shown that that catalyst part, I showed you that in a couple of slides ago, is a catalyst for water oxidation. So the pieces are there. There's another part to this story that I'll come back to. Our real target in this is carbon dioxide. Water splitting, as I'll show you, we've made progress in, and you'll see that. We're working very hard, though, on carbon dioxide reduction. It would be wonderful to make methane, but even the 2 electron products of CO2 reduction are interesting. To do this, if you look at the energetics, you really want to do so-called tandem cell design. You want a DSPEC that does CO2 reduction and water oxidation at the same time. So in an ideal system, I just showed you the photoanode, the place where water oxidation occurs. What you want to do is take part of the solar spectrum and use it to do that, have the other part of the solar spectrum go to the second electrode, a photocathode, where light is absorbed again by a chromophore catalyst assembly. And at the photocathode, a nickel oxide here would be a really good case if you could use it properly. The sense of electron transfer is different. Now you make the excited state, and electron transfer occurs from the oxide to the excited state. That then is then transferred to the catalyst, and that begins the series of events that leads to photoreduction. Now the reason why this is so appealing is, as I'll show you in a few slides, we know a lot about the 2 electron chemistry of CO2, and some of it looks like it might be viable early. For example, CO2, if you get CO2 reduction in a photoelectrochemical device like this one, even at 2 electrons, the product would be formic acid and formate, depending on pH, plus oxygen on the other side. There is a technology already in place for formic acid fuel cells, where you would have, as the fuel, formic acid going to CO2, with oxygen at the other electrode, which you could capture in the cell. That would produce a current, releasing carbon dioxide, which you could capture and run it back through your photoelectrochemical cell. This is not unrealistic. And you're not going to do this to power Tokyo, but you might do this if you live someplace where there's no grid. You know, you have no infrastructure whatsoever at all. So ideas like this may be more important than you think, at least for certain parts of the world's population. But here's, for us, I think, an equally important target, and that is the reduction of CO2 to syngas. What is syngas? Syngas is hydrogen. It's mixtures of hydrogen and carbon monoxide, because the technology's worked out under catalytic conditions to take them and combine them to methanol. And methanol then gets converted into hydrocarbons by so-called Fischer-Tropsch synthesis. It's all worked out. It's all worked out. So why don't we go back and look at one of these cells and see if we could use sunlight to make syngas and then plug it into a Fischer-Tropsch reactor. We're making real progress on this, and I'll come back and talk about that later. If you look at this at the very beginning, we have been committed to the notion that we really want to try to contribute to this problem and lay it out and come to reasonable solutions. And the idea is sufficiently far along that you can begin to see how this might happen. So we have collaborators who help us think about the techno-economic analysis background and so on. But look at this from the chemical point of view, and you could imagine the following. This is kind of an artist's rendition. You need a transparent conducting oxide backing. Then on top of that is a film of these nanoparticles. And this film is probably, say, 10 microns thick, 10 to 15 microns. It then is decorated on the outside by these chemically bound magic molecules. If you then translate that with light excitation and have one of these chromophore catalyst assemblies, so you get injection followed by activation, that could provide the basis of chemically bound to a cell that would begin to look like this. Here we'd have, as you can see, sunlight in, transparent backing, then a layer of transparent conducting oxide. And these are wonderful materials, as much as known about them now. And then on top of them, this layer of TiO₂ nanoparticles, then the chemically attached molecules. Sunlight in would produce oxygen on this side, liberating protons and diffuse through a membrane separator to go to the other side where protons go to iron. You can imagine taking this. In fact, one of our colleagues has published a paper on the economic feasibility, and consider reactors. What you can imagine in the end is a field, a photovoltaic field. And maybe 30% of that, in fact, has got pipes. And during the day, when the sun shines, hydrogen gets produced. You store it in a tank. When the sun goes down at night, you run it to an auxiliary power unit to generate electricity. This is economically actually very feasible and even appealing. Anyway, let's look at this now in a little more depth. I've been very abstract in general. Let's look at the parts of the problem. See if you can actually pull this off. So here's one of our chromophore catalyst assemblies. What do you have to do to make this work? Well, let's just walk around the problem. The semiconductor. I keep talking about TiO₂. We use other oxides as well, but it's a workhorse. Why? You've got to get the right band energies for injection and charge transport. You need to be able to do surface binding. If you have phosphonate derivatives of almost anything, at least an acid solution, they form relatively stable chemical bonds to the surface. I'll come back to this at the end, how to make this better. Light absorption. You need to capture as much of the solar spectrum as you can so your device can be efficient. Remember, we've got to have efficient devices that are inexpensive. Catalysis. It's okay to have a water oxidation catalyst. You won't have to turn over millions of times a year. And I'll come back to this. You've got to get the electron transfer dynamics straight. And by that I mean light gets absorbed, injection occurs, intramolecular electron transfer. But then there's something called back electron transfer that can cause big trouble. So let's walk our way through this, these various pieces, one by one. Oops, forgot device evaluation and scale up, which is beginning to spend or to consume more of our time. First, let's look at how this area has evolved in terms of chromophore catalyst assemblies. We treated this in our pH 11 and above. Another pathway appears involving direct attack on the oxide by hydroxide ion. And these are super fast reactions. But we know a lot about all that now. We're really interested in getting rid of the ruthenium in the end and going to first-rate transition metal catalysts. And this is just sort of progress made. And again, there's a subset of people working in this area. These are just some of our results. Nice example with a peptide complex. I'm in Shenzhen. We're a water oxidation catalyst. We looked at it in great detail, much like the ruthenium catalysts. Michael Coggins published a paper on this iron complex. There are a number of things the people have looked at iron by analogy with ruthenium, but you have to be very careful. And a lot of that work was done in acid solution with added cerium. And the first thing that happens is the complex decomposes to an oxide. So this is actually done in non-aqueous solvents with added water. Here's a recent copper-2 case, which is important because the reactivity of that complex is comparable to carbon. So we're spending a lot of time looking at copper-2 chemistry. What about the reduction side, reduction of CO2? If you look at this area and look at the mechanistic underpinning, ironically, perhaps because molecules were there on the shelf. First place we looked, we'd actually studied CO2 reduction many years before, but re-entered this area when I came back from Los Alamos. Here's a complex that Ken and his students know well. A terpyridine, a bipyridine, a ruthenium, and a solvento molecule. First studies done with acetonitrile, and what we showed was that if you look at this electrochemically, you first reduce it terpy, you then reduce it dippy, and when you do that with added carbon dioxide, you do get reduction of CO2 to CO. Mechanism involves dissociative loss of the solvent. It picks up a CO2. The electrons transfer from the ligands to make a carboxylic acid bound to the complex, this metallocarboxylic complex, which then in the end reacts with the CO2 that pulls off an oxide and CO comes out. Also showed with the same complex, if you had no CO2, but you had weak acids, and water would be a weak acid, that rather than do the CO2 reduction, there is no CO2, there's no competition, what happened was complex that came out of that reaction was the hydride. So reaction with water produced the hydride, different transition state, different pathway. That hydride then protonated to make hydrogen and recycled, and that was catalytic. And then we showed in acetonitrile, if you added a little bit of a weak acid, dihydrogen phosphate, under controlled conditions with some added water, you could in fact control the amount of carbon monoxide that appeared and the amount of hydrogen that appeared. Because they went through a common intermediate and you could dictate what happened. The key being this pathway here, as you add more acid, that starts to dominate. So we know all this in great detail. That led to the next result, which is potentially very, very important. And that goes back to this old friend, the carbene complex. It was the original water oxidation catalyst. It turns out to be a good CO2 catalyst as well. So it's very flexible. It does water oxidation and CO2 reduction. So in this experiment, what we did is we put the same catalyst on both sides of the electrochemical cell. There is an anion exchange membrane between them and a connector. If you apply a potential, and this is all done in aqueous solution, no acetonitrile. And in the end, all of this has to be done in water. The reactions have got to be done in water, just because they have to be on a massive scale. If you look at that, the net reaction is water plus CO2 doing what? One of our targets, syngas. Syngas. Oxygen comes out of the anode. Combinations of hydrogen and CO come out of the cathode. And not only that, you can control the relative amounts. It turns out syngas in different ratios is used to make different products. If you have a fixed potential and increase the bicarbonate concentration in the CO2 bicarbonate mix, you can control the ratio that way. Or you can control the potential, change the potential, and control, dictate the products. If you look at this cell, the way it operates, 1 millimolar complex, 1 to 2 milliamps per centimeter squared, 50% energy efficiency. We're in the process now of scaling this up through using flow-through reactors. I think there's a chance this would become of interest economically. Let me come back and show you what I mean by flow-through reactor by introducing another chemistry. This is in collaboration with Maurice Brookhart, one of my faculty colleagues at UNC, a famous organometallic chemist, and Quan Kang. They showed that you could take this pincer complex of iridium, this is acetonitrile complex, with some added water, and when you reduce it by a couple electrons, it goes to a dihydride. The dihydride now undergoes a rapid reaction with carbon dioxide to make a formate insertion, to get an intermediate formate. And you can see all these under the right conditions. It then solvolizes off the formate, goes back to the acetonitrile complex and recycles. And here you see catalytic currents as you add more and more CO2 to the solution. Rate constant is pretty respectable. The rate constant, this thing turns over in 50 milliseconds, so it's pretty fast. So that's observation number one. That's pretty good for the second CO2 reduction product formate. But Pond took this 2 steps further. By putting on this aminium tag, he could now make the catalyst aqueous soluble, and he did. and in aqueous solution discovered under the right conditions, that is, don't make it to acidic, it's very simple, that you can, in fact, reduce CO2 selectively to formate with no CO and no hydrogen. In fact, in aqueous solution, this thing is selected to make formate. So water is a solvent, it's fine. Throw away your acetylnitrile. The next step that Pong has undertaken in collaboration with a couple other postdocs is to make high surface area carbon electrodes. Notice he's now taken a pyrene and attached it to the pincer ligand. This is kind of standard stuff now to get things that absorb the carbons. So he's huge high surface area carbon electrodes with a flow-through reactor, and he can make huge amounts of formate in a short period of time. So we're anxious to pursue this and see how far we can take it. But let me go back here at the end and finish the story about water splitting. Here is, again, one of these catalysts. This is, again, that favorite carbene catalyst. I'll still use it again, but now instead of having a bipyridine as one of the ligands, I've gone back and done the synthetic chemistry to have phosphonates. That means that everything I did in solution can now be translated to an oxide surface. So that's great. I want to have a device, I have to have things on surfaces. I have to have an interface. And here, in fact, is a scanning electron micrograph. This is an underlying transparent conducting oxide. Notice all these nice particles. This is what a TiO₂ film would look like, but this is not quite that. What this is are nanoparticles of one of these transparent conducting oxides, namely tin-doped indium oxide. So these little nanoparticles, this film conducts electricity. So we can coat that with our catalyst. You can see through it, you can do spectrophotometric experiments, control the potential, and you can do water oxidation catalysis, but you just increase the surface area by 500 to 1,000. Great stuff, same mechanism, small problem, surface attachment, right. But as the pH goes up, what we find is that these nice phosphonate links that are stable in acid are unstable in base. The complex just hydrolyzes off the surface. Kind of standard ester chemistry. To solve this problem, we turn to atomic layer deposition. First, in collaboration with Greg Parsons of North Carolina State. In this experiment, you take an oxide surface and a highly reactive precursor to a stable oxide, in this case, trimethyl aluminum. The trimethyl aluminum hits the surface and sticks, and you now have sort of an oxide aluminum, and you still have methyl groups. The next step, you add water and hydrolyze them off to make methane. Next step, you now have the beginnings of an oxide layer. And you can build layer after layer after layer. It's a gas phase technique. It's totally conformal. It goes completely through these films. Great. And then you recycle. First value to this back of the surface stabilization is here. Same carbene catalyst, but now in two versions. One, just a version on a surface. Now I've increased the pH to pH 11. So this complex doesn't have a chance on the surface. Undergoes rapid hydrolysis, you can see that. If you put it on the surface and hold the potential high enough to do water oxidation, the current starts high and it just collapses. The stuff's coming off the electrode. With this one, we first bound it and then did ALD, atomic layer deposition, layer of titania or alumina, and then these phosphonates become part of a matrix, a mat across the surface, and they're stabilized. And here you can see for an extended period, water oxidation, and it goes on and on. There's something else that's notable here. The rate constant you derive from these kind of data is about 10 to the 4th. There's a rate enhancement here of 100,000 compared to acid solution because of these atom-proton transfer reactions. Under those conditions, that's 10 times faster than photosystem 2. Very simple, complex. Control the conditions, control the reactivity. Just quickly, another way to stabilize surfaces. Turns out, put down the complex, and my postdoc, my Korean postdoc, is looking at stabilization of surfaces that way. This is published recently. I won't dwell on it. Let's finish the story. Let's do water splitting. And let me go back to this assembly that I've mentioned all along, this one. It's got the carbene, it's got this ruthenium with phosphonates, and now it's on a surface. First electrochemistry. So this is on one of these nano particle things. Here's a cyclic voltammogram of that assembly on that material. Increase the potential. There's a ruthenium 2,3 wave, the 3,4 wave. Great. Then there's a wave here for oxidizing the chromophore, and that triggers water oxidation catalysis. That triggers water oxidation catalysis. So the assembly is perfectly capable of doing water oxidation. Now let's go back and ask the big question. Assembly's there, the reactivity's there. Let's revisit this issue of how you, in fact, can get light to carry out this reaction. How do we go about that? And so let's look at some numbers. And at first glance, it's very discouraging. One thing about the numbers that's quite remarkable is the difference in time scales. Excitation, injection occurs in the femtosecond time scale. We want to stabilize surface bonding indefinitely. So there are time scales that we're dealing with here that could go from years to femtoseconds. But we know about microscopic dynamics. I already showed you how we know that. And so we know we get fast, efficient injection, intramolecular electron transfer. But then look at other numbers and look at the sun. The sun, if you look at its rate of output, excites one of these assemblies every second or two, no more. That's all the sun has to give. It's slow as anything. It's a terrible light source. So what happens? Photon comes in and gets absorbed. 100% injection efficiency, great. We oxidize the assembly at the catalyst, wonderful. Then there's a competition. The electrons have to drift through the TiO₂ to get to the underlying conducting oxide in competition with back electron transfer. I keep talking about that. Now you'll see why. In these thick films, say 10 to 15 microns in the end, it takes milliseconds for the electron to drift all the way through the oxide. It's very slow. It's a semiconductor, but still it's slow. Back electron transfer occurs on a microsecond time scale. What that means is that for every photon that goes in, if you look at these numbers, one photon gives an excitation event, that's great, injection, yep. But 1 out of 1,000 times, or 999 times, the electron drifts back. And so we have back electron transfer. So we're in big trouble. This whole thing, if you look at these numbers and think about the dynamics, cannot work unless you do something else. And what we did now to do something else was go back to atomic layer deposition. Because what we said is, wait a minute, think about this a different way. You've got this material, nano-ITO, this conducting oxide now in a film format. Go back and use the atomic layer deposition one more time and put a very thin layer of TiO₂. You don't need a thick layer. That's fast, the TiO₂ is slow, so make that very thin. When you do that, and this, by the way, shows a transmission electron micrograph that shows on the outside the shell of TiO₂ on a core of nano-ITO, core shell. What happens now, and we show this by transit absorption measurements, excitation, injection of the TiO₂, rapid electron transfer on the nanosecond time scale, not the millisecond, because the TiO₂ is so small, and the electron transfers to the FTO and out of the system. And when you build a device of that kind, you get sustained photocurrents. If you look at the per photon efficiency on a per photon absorb basis, it's not spectacular. This is the first experiment there. It's not bad. Still, it's between 4 and 5%. Solar efficiency is about 1.5%. But if you keep going and we continue to go, let me just show you the state of the art here at the very end. State of the art here is, all right, keep everything the same. We need this core shell structure. That's great, but there are other things you can do. For example, here's an experiment where instead of the nano-ITO on the inside, we put tin oxide. Then a thin layer of TiO₂. The reason we do that is that it turns out if you look at the potentials of the two materials, when you inject in the TiO₂, the electron that goes down in the tin oxide, there's a 0.4 of a volt difference between the two. That means The back electron transfer, once injected through the TiO₂, has to go uphill 0.4 of a volt. All of a sudden, the efficiency jumps up to 20%. And here you can see sustained photocurrent, and here direct measurement of the products, hydrogen measurement, oxygen present, using microelectrodes. So we're well down the road here, I think, to doing water splitting, and I think we put all the pieces together, at least in a way that people can follow and improve and make well. Let me finish with acknowledgments. This work was done in the UNC Energy Frontier Research Center. These are centers funded by the Department of Energy, Basic Energy Science. This is a happy, smiling group in the Energy Frontier Research Center. This is a collaboration. It's mainly at the University of North Carolina, but we have an outpost in Florida, one at Georgia Tech, and now one at Emerald. And this is my sports car. Notice the license plate right there. Thank you.